Okay, well, it's my pleasure to introduce Tomáš Jakl, who's going to talk to us today about canonical extensions, I believe. Is that right?
Yeah, something like that. Yeah, I actually don't remember the title. Thanks for having me. Yeah, so this talk is going to be about canonical extensions. I have two disclaimers already from the start. So first of all, I'll be presenting stuff that I was working on roughly 3 years ago. So it's a bit rusty. I tried to recover everything, and I might come back to it. So I thought this is a great chance to come back to it now to revise for the talk. Also, because I'm new here, everybody wants me to talk, and I don't want to repeat myself too much. So that's why I picked some older topic, because otherwise it would be like a talking machine. So that's one. Second is I made 6 sheets of papers of notes, and I usually make 3 for a 1 hour and half long talk. So can't promise anything. I don't know if we can get to the applications that I intended to show you, but at least I hope to show you some beginnings or some overview of canonical extensions. As far as I know, this is a seminar about C-star algebras mostly and related topics, right? And this is a talk about lattice theory and duality theory. So there is some similarities, but I don't really know the shared background. So please fire away any questions you might have. Also, I think I've noticed there is some canonical extensions in somewhere else, that in some other discipline, maybe C-star algebra or somewhere else, it does not have to be related to. So I will define everything we'll need. Yeah, and so let's get into it. I wrote here some references because it takes long to write. And the theory originates with these 2 papers. It's by Bjarne Jansen, Alfred Tarski, Boolean algebras with operators 1 and 2. There's a nice historical survey by Mike Gerke and Robert Goldblatt. They have these 2 papers over here. But the presentation I'm going to be taking mostly goes to this Mike Gerke, John Harding, bounded lattice expansions. I think this is the cleanest or the most polished treatment of this theory. So as you see, this is spanning over 50 years, right? And for some time, so something was done in the 50s, as you see, and then people were basically using it, but it got another kick off in the 90s where people started studying it more abstractly. And so this is what this resulted in. It's kind of more general, more abstract approach to this. All right, so where does the theory originate? It originates in duality theory for Boolean algebras, right? So you might have heard of stone duality, at least a little bit. You might have heard of Boolean algebras. Okay, so we'll start with that. So what's stone duality? I'll review a few types of dualities, and then we'll get to the problem where this comes from. So Boolean algebras are algebraic structures. They are lattices with a negation, basically. All right. And they were shown to be dual in some sense to what is called stone spaces. So that was Marshall Stone, actually published it in a journal of Czechoslovakia in 1938 or something. So that's why the duals are named after him. So these are stone spaces, so-called stone spaces. Actually, sorry, this paper was about distributed lattices, was published in the Czechoslovakian journal. The first one wasn't. All right. And so it is a duality in sense of category theory, but it's not too important for us. So whenever we start with a Boolean algebra, we can build a stone space. So what is a stone space? That's a compact Hausdorff space, which is 0-dimensional in any zeroness type of dimensionality you can think of, probably. So let's say the basis is a form of closed subsets. All right, the closed open subsets of the space form a basis of the topology. Right. So when I give you a Boolean algebra, I can actually give you a stone space, build a stone space out of it. the way this is done, so I need a set of points. These will be ultra filters of the Boolean algebra, and then I need some topology. So ultra filters, these are filters, so that's upwards closed subsets, which are closed under finite means of the lattice. And you also have the property that if you have for every element A, either A is in the ultra filter or the negation of A is in the ultra filter, right? Okay, not missing anything. Right, and so these are just particular subsets, and the topology is generated by the sets that look like this. So if I have an element of the Boolean algebra, I will put this as into the basis. So it'll be this, this is a set of ultra filters that contain the element A. All right. So this forms the basis of this topology. These are the points. So this is one way of building the duality. The way back is much simpler. If I give you a stone space, all you need to give me a Boolean algebra is just to take the closed open subsets of the space, and you just order them by inclusion, that forms the Boolean algebra. So you have intersections as the meets of the lattice, unions as the joins. The empty set is the bottom element. All of the points are the top, and the complement, set theoretic complement, is the Boolean algebra complement. All right. So this is the basis. The point is, if you go there and back, you get an isomorphic object, whichever way you go. So that, and also this extends to homomorphisms here and continuous maps on the other side. All right. So this was the basis that started so much research. Namely, this was later extended to distributive lattices. So you will have something that is called Priestley spaces. And distributive lattices. Just write this. Yeah. Was there a question? No. And it works similarly. You build it on prime filters, and you have to add an order. So you will put these are stone spaces with an order that separates points. I don't want to go too much into the details. And backwards, you can't have clopens wouldn't be enough, so you or would be too much. So take clopen upsets because these are ordered spaces now. All right, so that's one difference. And then so that's one way of extending it, and you can decide to keep generalizing this side of the equation. All right. The other option is to say I want to maybe not have structures with topologies. So that was done. It's in some sense a trivial generalization of this, which is called discrete stone duality. And so here we just have sets and functions. And here we take, I will write CABA, well, that's complete atomic Boolean algebras. So complete means it has arbitrary suprema of elements. And atomic, so atoms are the elements that are just above the bottommost element. So everything that doesn't have anything between itself and the bottom element, that's an atom. And atomic means that atoms generate the whole thing by suprema. Right? So atoms go and generate. All right. And now this might seem like sort of a trivial exercise, but it really is, it works out. So if I give you a set, there, yeah, you start, I don't, this is the usual shorthand, right? But you need completeness first. Yeah. And then. That's why I say that. Oh, because that's the Polish way of thinking. Backwards. Sorry. All right. All right. So if I have a set, I can build a complete atomic Boolean algebra. Any guesses? Oh. Exactly. Yeah. It's that trivial. So you just take the set of all subsets, ordered by inclusion. So it's a complete Boolean algebra. And what are the atoms? The singletons, exactly. So this would, something like this would be the atom, and obviously that generates the whole algebra, right? And backwards, if I give you such a Boolean algebra, you just take the atoms, and that forms a set, surprisingly. But the point is, if you go there and back, you get the same thing. All right, so these are now 3 dualities, right? That's nice. We have always something algebraic on the right, something sort of topological, something set based on the left. There are many, many, many ways to extend this. But one question useful for people studying logic was how to extend either this one or this one, the one about Boolean algebra, for structures that are important in modal logic, for example. So you would have an algebra, like a Boolean algebra with an extra structure on it. So these were called modal algebras, for example. And this is what inspired this paper by Bjarne Janssen and Alfred Tarski. And just for simplicity, because I mentioned modal logic, so we will only, for now, be interested in when you have a Boolean algebra and one operation, which is unary. So let's call it diamond for no reason, or for a particular reason, depending on your background. But so we just have a unary operation, and we might assume something, I don't know, for example, it preserves binary joins and the bottom element, right? But that's not too important here. But this is the usual thing. This might be giving you a model of certain modal logic, sort of an algebraic model. And now you ask yourself, okay, so we have this, but there is nothing about join preserving operations here, right? Can we extend it in some way? Can we build some kind of duality the same way we did here, but for Boolean algebras with some extra structure, right? What do we do? What do we do? It's not so obvious, unless you've seen it, and then it's obvious, and then you can't forget it. But I'll tell you what Janssen and Tarski showed. So they said, okay, so in order to build this structure, we can actually embed this B into a bigger structure, where that would be the extension that we will be speaking about, where also this operation lifts, and then we'll be able to describe the duality theory from that. All right. So what do we do? They noticed. I don't know if that was a known construction already back then or not, but if you have your Boolean algebra with an operation, you can build just a structure with a binary relation. So we will have, we will have some XR, where R is a binary relation. Explicit. All right. So X again will be the ultrafilters. So that's like points of the stone space, right? and R will define from this diamond. So if I have X and Y, so these are some ultrafilters at this point, I will say that this is in the relation whenever I take diamond of some A for A that was in the ultrafilter Y, but when this forms a subset of X, all right? So you don't have to worry about this too much. It's just that it is a simple first order formula to write down some kind of relation out of a Boolean algebra with an operation. All right. So this is the first step they did. And then they noticed that for these type of structures, you have also a similar kind of thing where you recover a Boolean algebra. So now when I start with X and R, which has a binary relation, right? I can build a Boolean algebra. And now we don't, because I'm at this point just talking about a set, no topology here. All we can do is just pretend we have the discrete stone duality. So I just take the power set, and then I need some operation on this Boolean algebra, right? So I will define it. Where do I have it? Call it like this, and I have such operation. I apply this unary operation on a set, on a subset of X, and I get the set of points such that there exists a Y, so that I move from R to this Y, and Y is in this set A. Right? So you might have seen this before. No, that doesn't matter. Now, what happens is, right, you would expect, as we had this pattern there, you go there and back, you go there and back. But here, when you go there and then back, you're not getting the same thing. Right? That's even not surprising because we built ultrafilters, and then we take the power set. We don't take clopens, right? We can't even have the same sort of Boolean algebra. But what we got here is a complete atomic Boolean algebra, right? So somehow, so if I call this operation like applying like bottom plus and here top plus, so then if I take B and I take B, I make it into a relational structure, and then I turn it into this complete atomic Boolean algebra with this extra relation. Turns out this original B I started from embeds into the big one, right? Right. So this was the basis of the construction of Johnson and Tarski, right? Hopefully I won't get any more technical. And somehow it combines the discrete and non-discrete duality, stone duality. And that wouldn't be so interesting, but what they prove? So they proved that every completely joint preserving operator, so imagine you have such a thing here, but it preserves all joints, all right? And if it also sends the elements of this that are, in the mapping here, two elements again of the same form. So in some sense, it restricts to an operation here. Then there is only one way this could have been created, right? So imagine you have diamond here, and you have some kind of extension of it here that preserves preserves suprema. There's only one way to extend it here if it distributes. Also, equationally definable properties here, some of them, lift to over here. So somehow this is some kind of sound extension. But when you think about it, this one has so much more structure in it, like somehow it also contains the information about the ultrafilters. These are there as well, also the clopens. Somehow we got into a bigger setting, which is richer, more descriptive, and we were able to lift the operations from here to there. All right. So this then they used as a basis to give semantics, relational semantics to modal logic. I will not go into that. They did that by adding something like a topology to this, and then that was good enough. Anybody knows what these are called? General frames, or I forgot. Anyway, right. So this construction was the basis of Jan Santarsky construction. All right. Now, as I said, some 30, 40 years passed, and people started asking, where does this come from? All right, this is useful. This is giving us a lot of useful results. But can we say something about what does it actually do? Because when you think about it, we have a Boolean algebra, and we build a new Boolean algebra, right? Why do we have to go through the spaces even to do this? All right. And it turns out that there is so much interesting stuff to say. So that's what I will do now, unless you have some questions. All right. So at the moment, this is not a duality, right? We just built some kind of extension. And if we wanted to do duality, we would have to add extra structure on this. So hopefully, where I'll get is to tell you at least how you would derive for yourself the structure so that you have a proper duality like we had here between stone spaces and Boolean algebras. So you would imagine you would have something like Boolean algebras with a unary operation and stone spaces with some kind of binary relation, for example. And if you wanted, you could have even more complicated operations here, could be mixed arities, could be even between different structures. So like A, B times D to C or something, and monotone in the first and not monotone in the second. You can do these sorts of stuff. The reason why, by the way, I decided to talk about this topic here is I somehow thought it would be interesting if you've seen not necessarily this, but also probably what I'll show you later on, some kind of thing like that somewhere else. Because as far as I've seen, this is only in lattices, but maybe I'm missing out on some other parts of structures that can do something like this. All right, so if you can think of anything like that somewhere else outside of lattices, that would be cool. All right, so what have we done? So you might notice that yes, we talk about here we talk about relation and the operation, but for the general for what this is doing, that's not so important, right? We start from Boolean algebra, we take the ultrafilters of it, and then we take the power set, and we can embed the Boolean algebra into that. I might write it explicitly. So I have the power set, the ultrafilters of a Boolean algebra, start with the Boolean algebra. And if you give me an element, right, what do? I give you the set of ultrafilters that contain the element, right? That's the embedding. All right. But we also can notice, right, that what we actually might decompose this. So how about we split it in two parts? Imagine, so we had this operation that gave us the basis. These were the basic elements of the basis of the stone space. So we put here the topology, right? So actually, so this embeds into the topology of the stone space of B, and this again, and then that's just inclusion, right? So open subsets are obviously just subsets of the space of ultrafilters, right? And now with this, all right, this is a lattice. These are Boolean algebras. It's like this. Right. So this B, you see, as we define it, this forms a basis when embedded into the topology, right? So everything here is joint generated by the elements of the basis. These are just unions of elements like this. So this is joint generated by these elements. Right? So joint generated by B when I see this embedding as just embedding, right? And these things are intersection generated by the opens, right? Why is it so? In the topology, we have open sets, and as we know, every singleton in a Hausdorff space is closed, right? So in particular, every complement of a singleton, which looks like this, will be open, right? So any set we can think of, we just get as an intersection of these things, right? So we see by composing B join meet generates this lattice, or sorry, meet join generates this lattice. So if we take joins of everything in B and then we take intersections of such things, we get all possible subsets of the set of ultrafilters. All right. So this is something that they've noticed very early on. And so they describe this, I'll just call, let me just finally start using the symbol that is being used usually. So this is this B delta, B delta. That would be either this or this, right? Let's just call it B delta so that I don't have to write such a big complicated expression. So what they notice is that they can describe this abstractly. So they can say, okay, so I have B, and this is embedded in a bigger, so that this is just a Boolean algebra. It just has finitary joins, finitary meets, so that might not be as rich, but this then embeds into a complete Boolean algebra. So that's a Boolean algebra. It has arbitrary joins, arbitrary meets. Moreover, this is meet join generated by B, and moreover, this is a complete atomic Boolean algebra, right? So everything is generated by atoms. And this is the definition they worked with initially, I think. So for a long time, that was enough. And you can just work with this abstractly. You don't have to now think about how this was constructed. And later, so this is finally the last reference. They realized they can describe it even slightly in slightly simpler terms. So this is a theorem of, I think it's Harding and Gerke. Right. Yeah. So, but maybe it's a combination with Johnson as well. So let's say these three. All right. So you have Boolean algebra embedded into another Boolean algebra such that B is complete. B join meet and meet join generates d delta, and there is a compactness condition. So that is if you have, let's call this embedding E. So if you have meet of some set S of elements from B less than join of some elements of set T of A of B, then there must be some finite subset of these two sets for which this is already true. All right. So they notice, first of all, this property, and second of all, for any B into C, which satisfies conditions of one, there is a unique isomorphism between these two embeddings. So this is unique up to a unique isomorphism actually. All right. So maybe I should say where is this other one where does it come from? So we discussed that this is meet join generated, but you can also go the other way around. So if you take any such element, not only it's open, but it's closed, right? And then if you take intersection of closed elements, you get singletons, and then join of singletons obviously is any set. So that's why it's also the other way around. So that's where this comes from. So it's such and such. All right. So this is an abstract setting now, and another theorem by now definitely Gerke and Harding. They actually provided a construction that doesn't go through the spaces at all. So it just uses some adjunctions, filters, and it's actually for those that carry it's constructive, it doesn't even need the choice, the axiom of choice. All right. And over the years, this was generalized to, so this is, as I presented, only Boolean algebras. You can do it for bounded distributive lattices, or just distributive lattices, or just lattices. They don't even have to be distributive. All right. So, and now this is actually all you need to know. So now this would be called the canonical extension of B, and all you need to know is these properties. And it turns out it is as expressive as talking about the stone space. It contains all the information you might need. And you can reason just algebraically about the canonical extension. We don't have to know how it was constructed or what it represents, but it's useful to know that. All right. Now what I would like to tell you is how we recover, at least from this description, the stone duality back. So this, Gerke likes to call this a point-free stone duality, but there are other point-free stone dualities, maybe algebraic stone duality, or maybe, what was the other one? Algebraic. So there is, now, whenever you have a Boolean algebra, you know this can extend to a unique canonical extension, and you can reason about it this way. So The question is how do we recover these stone spaces, which once we do that, once we have this correspondence between Boolean algebras and stone spaces via canonical extensions, we can ask these questions. What do we do with extra operations? How do we use this to describe the extra operations on the space side, right? And many more things. All right. Right. I'm actually on time. I didn't expect that. All right. So I think it's useful to still continue building this intuition of how we build this before we can completely free ourselves from how we build this. So get back to this picture. I have B, which is embedded into the topology generated by the elements of this form. And then this is just embedded into the power set algebra filters B that we would like to think of as the canonical extension. All right. And now, first of all, we have these open sets embedded in here. What do they look like? If we only know these elements be embedded in here, how do we recover these back? So as we said, these are joins of elements like this, but actually if you take, so if I give you any collection of these elements, and then I close it down under everything that was there, I still get the same join, right? Between those two things. And I might also take the same thing as I had here and I add finite joins, and it doesn't change the big join of the whole collection. So intuitively, it makes so much sense. These correspond to the ideals of the Boolean algebra. So that's subsets of B that are downwards closed and are closed under finite joins, right? And as we discussed, we also had some specific elements that are open and that we need for the construction. That those look like this. So these are still open because every singleton is closed in a Hausdorff space. But these are open. So what do they correspond to? And it turns out these correspond to prime ideals. So it's actually the complete complement of an ultrafilter, right? If I have an ultrafilter at the complement, that's an ideal. So just call this prime ideals. They correspond to elements of this form. Okay. And now we can go completely dually. Oh, all right. No, so that's one step, right? So we describe everything in terms of the original Boolean algebra. In terms of the original Boolean algebra, we describe the open set as ideals and the sort of mid generators as prime ideals. But if we are thinking only in terms of this lattice, so now we try to abstract ourselves from how we constructed everything, right? So we now think about just this. Then this corresponds to some specific elements in here, right? So we can write this as the I elements. We can call them open elements. Why not? And these are just elements that are obtained as a join of elements from B. So I mean, it's the same thing, right? But you can view that as elements U in the canonical extension, for which there exists a set in B such that U is precisely the join of that set, right? Right? And in the same spirit, so now we're slowly abstracting ourselves away from this construction again. In the same spirit, we can describe these points. And it turns out, we will not do this exercise, but these correspond precisely to what is called completely mid irreducible elements. So I'll just write it like this. Oh. And this is a definition that you can define for any complete lattice. So these are elements M, where if you have a big mid of anything below M, then there must be some element S in the set S such that S is less than M. Right? So completely mid irreducible. So all right. The point is to build the vocabulary, right? So now, if we are in this setting, instead of speaking about opens, we could speak about ideals, but we will prefer to just speak about open elements of B delta, which is anything that would be obtained as a join of an ideal. And instead of speaking about elements of this form, we can just mention the completely mid irreducibles, which are just elements that cannot be, you can say, decomposed by anything from above. Right? And now completely analogously, you can do the dual. So instead of closed subsets, you would have filters. And instead of singletons, you would have completely join irreducible elements. Right? So maybe you can have here the glossary. So topologically, algebraically, and extension-wise. So opens, ideals of a Boolean algebra, and or distributed lattice, or the I elements closed correspond to filters, and we can call this K, because that's the usual symbol. I don't know why. Oh yeah, from compact. So some people call them compact, which makes sense. Then instead of x minus point, here we would have prime ideal, and here we just would have completely meet irreducible. And now here instead of a point, a singleton, we could have prime filter, or which in case of Boolean algebra, that's exactly ultra filter. And that would be a complete dual definition to what we had before, completely join irreducible elements. All right. So with that in mind, now when you think about it, what do we need to, if I have a Boolean algebra, what do I need to define the corresponding stone space like here? Right, so there was ultra filters and opens, right? So we have that. So we can say, okay, so we will, starting from a Boolean algebra, we take its canonical extension, then we use the choice to have either these or these, it depends on us. Those exist. And we will say, okay, so we built a new, we built a topological space that will be on these elements, all right? And as a topology, we take elements from here. And we will know that A contains precisely those, you know, it has to sort of, in order to, now I have to think about it. You have an open, and you want to say that X is in the open, that's equivalent to saying that U is not a subset of, you know, X minus a point, right? So I guess, right? So now if I have joint irreducibles, or meet irreducibles, which we know correspond to these things, so I will take all the meet irreducibles such that my A is not below M in this complete lattice. That's it, right? So I'm just translating. All right. And that's a choice. You could equally base it on joint irreducibles. There is an order isomorphism between the two, and you do the other obvious thing you could do, right? So now, what happened here, right? So we have a Boolean algebra, and it sits inside a complete Boolean algebra in a very tight way, because if you had any other Boolean algebra in which it would sit the same way, it would have to be isomorphic to it, all right? It's very tight. And this complete Boolean algebra actually completely contains the dual of the Boolean algebra. So this extension both contains the Boolean algebra and its stone dual. So now when you reason about anything in terms of the duals of the Boolean algebra, you can just use this and combine, you know, your lexicon from the Boolean algebra and the spaces in one setting, right? So now we can finally try to see what happens if you add some operators here. How would you obtain a duality for extensions of Boolean algebra, right? From this setting. Because this is the thing. The power of this to me is, right, so this is a nice theory, but we can completely forget about it. And actually, that's what people did for most of the time when thinking about dualities. They were attempts to extend this stone duality in many ways, and people would just guess, right? So they would guess some extension, and they try hard, and maybe it didn't work, so they will kind of get an intuition for why it didn't work, and then luckily at some point they get to a point that go like, okay, so this would be the duals, right? And again, you can like every single time guess basically, but with this guides you. It tells you what you have to do in order to get a duality, and is very powerful when you're trying to do completeness of some logics. So you would have some logic, so that corresponds to Boolean algebras, some extra operations on the logic, or maybe quantifiers, or maybe modalities, or whatnot. And then completeness tells you that we've captured everything. We're not doing things arbitrarily. In particular, just to those don't know that know a little bit of modal logic. So modal logic has is known as sound with respect to the structures we talked about, just a set and binary relation. But that's sound, but it's not enough. And in order to be enough, you have to add extra structure. But how do you get that structure? Again, people tried and very hard and figured that you have to either add topology or make everything finite, right? But this explains why the topology is there. Okay. All right. So, I mean, I keep talking and nobody's asking, so maybe.
So when you say this guide you when you're looking at extensions, it's sort of like
Mhm.
we're talking about social algebra where you have Boolean algebras with extra operations, which correspond to some modal operations.
For example, yeah.
For example, but on the topological side, you're talking about stone spaces again, I guess, with some extra relation.
That's what you would guess based on the 40, 50 years of research, or maybe 70 now, actually. But that's what we guess now. Like, okay, so there's going to be some relation, but it doesn't have to be. And actually, if we get to it, there could be other. It could be like a partial operation. That's also good enough sometimes.
Partial operation also.
Yeah, those are semi-continuous.
That's always never.
Well,
Never
if you start with a Boolean algebra, then that's the most natural thing to do. Yes, because right, that comes out of this. If this is your point, then you will have a Boolean algebra. And also, this procedure is fairly general. Also, this construction here, as I said, you can construct this abstractly. You can use some kind of adjunctions, but there's also some kind of completion construction of this. So there are like 3 different ways to obtain this constructively. And so potentially that tells you how to extend this whole theory to other classes of structures, not just Boolean algebras. So it already could be used for lattices, but maybe there are other structures. I don't know, MB algebra. Oh, all right. Okay, so we have the glossary. Now we get to the operations. All right. This is where it all shines, I hope. So we get back to our original question. So imagine, and just for simplicity, I will have, let's say, 2 Boolean algebras and an operation between them. It might be what we had before, some kind of diamond, and then A would be the same as B, or it could be homomorphism, or it could be anything in between. Right. And I promise to you, we will assume that it's monotone. There's a lot of the theory that works. I mean, it was extended for non-monotone maps as well, or not antitone even. But for now, let's assume it's monotone. And now I promise to you that this could be extended. So if I have such an operation on Boolean algebras, I can extend it to canonical extensions. And this extension will preserve equalities, some equalities. I will not get to it, partially because also I haven't prepared this part. And I never needed it. But there is a lot of stuff that can be said about extension equations that are preserved. All right, so now if I have such an operation, can you imagine how that could be extended? Extended in the sense that it would commute like this, right? So maybe write it like that already. We have these embeddings, right? That exist into the canonical extensions. And now, can you think of extensions of F into this setting? And I tell you, all you need to ever think about it, not this construction, but just this. We have a Boolean algebra, some kind of completion. So this is complete. And B join meet, and meet join generates B delta, and it has this compactness property. Right? You don't need to know anything else. All right. And you scratch your head for about 5 minutes, you'll realize there are two most natural things you can do. Right? So these sit inside these original elements, so you can use them either to join extend first and then meet, or meet extend first and then join extend. Right? So let's do that. So sigma extension is the one where you first meet extend and then join extend. So if I give you a compact element, so this is the one that's obtained as meets of elements in A. I will define F sigma or sigma on K the obvious way. So this was meets of elements in A. So that's how when we make use of this F, so it will be F of A for elements A in A that are above this K, right? Because that's the elements above K uniquely describe it, because this is just meets of elements A. Right, so that is one step. So now we've defined this map F sigma for compact elements. And we know everything here is join of compact elements, because these are all the ones that are meets of elements in here, and we know everything is join of meets of elements in A. Exactly. Right. So now if I give you an arbitrary element of the canonical extension, the sigma extension will just do the join of the sigma extensions of compact elements, right? So that would be compact element closed that is below of U, right? So that's the obvious thing. And there is a pi extension, and that's exactly dual. Here you would put the ideal element. You would start with joins, and then you would end with meets. So pi extension. Also, not write it properly. Also has this type. So they both are of this type. So we now have two extensions. And I forgot which one is bigger. So there is some stuff you can say already about their relationship. One is always a little, less than or equal to the other, but they both commute like this, and that's clear. And there are some very basic properties that we will need today. First of all, if F preserves binary joins, then the sigma extension preserves non-empty joins of any size. Right? And dually, you have the dual one, right? So if F preserves binary meets, then F phi preserves non-empty arbitrary meets. No, it's arbitrary except for non-empty. And this is the interesting one, if F preserves finite joins or meets, so either of them. So this is exactly this plus preserving zero, or it is precisely this plus preserving the top element. So either the bottom or top on top of what is already here. Then the extensions actually agree. So F phi is equal to F sigma. All right. And in that case, we just call it F delta. All right. This is one ingredient. All right. Now we're one step from being able to recover the relations as well. So bear with me. Not the paper I want. But before we do that, let me tell you one more thing. So if you know something about order theory, lattice theory, you know that functions between complete lattices that preserve all joints or all meets, which happens in this case. So if F preserves binary meets and also the bottom element, then also the extension will preserve the bottom element. So then that means it preserves all joints, not just the, even the empty one. So not just non-empty. So in that case, it has something which is called the right edge joint. Right. So if F preserves finite joints, there exists F hash or F sharp. It should be sharp. It's flat and sharp. And that has the property. So it's a right edge joint. So this is all that this means. So U is less than V if and only if U is less than F sharp V. Right. So U is less than V if and only it's less than F sharp V. Right. And so there's a simple fact. And in this case, F sharp preserves completely meet irreducible elements. That's this M infinity. So F sharp, it's of this type, right? So it goes backwards. So it's from B delta to A delta, but actually, because it preserves these elements, that means that it restricts to B delta to M A delta, right? And so this would be the continuous map that is dual to homomorphism, for example. So we are building the dual. Imagine this was a homomorphism of Boolean algebras. Then obviously that preserves finite joins. And of course, it preserves all the other things. And so this would be the continuous map, right? Then that would be between these spaces. If we put a topology on it, like here, this would be the continuous map that recovers the homomorphism backwards. Anyway, so the fact is, and this goes back to the Johnson-Tarski theorem, this original F is fully described by the property of or this this F, sorry, which was it? Yeah, F sigma is the unique extension of F if we know that it preserves non-empty joins and its right adjoint maps points to points, or meet irreducibles to meet irreducibles. And now we can, so now imagine actually F was our diamond. Right? So that was what we started from. That would be some kind of operation that precisely preserves finite joints. So that was preserving this N0. We would build this space, right? V delta with this topology. We would put a relation. And how would we define the relation? X is related to Y if and only if right adjoint maps X below Y, right? And now return back to what I just said. So we know F is uniquely described by the extension that has these particular properties. Also, extensions uniquely determine itself. And also, since everything is joint generated by the meet irreducibles, so actually enough to just use the meet irreducibles. So in this case, it's a very specific situation. This is all you need. So then if you have this relation, this is all you need to recover back the modal operation, right? So that's some kind of completeness. If I now write down the properties that this has, right? So some kind of topological properties, I would fully describe the class of the stone spaces with additional binary relation that are dual to Boolean algebras with modality, right? And it would be something like if I have an element like if I take, so that's for example one property. If I take the set of elements that X is related to, they form a closed set, for example. There's a couple of more things like that. All right. So, but this sort of guides you what is needed, because we know everything is determined by that, and that's determined by that, but that's determined by that. It's kind of chain of necessities in order to describe this. All right. What am I? All right, I've last 15 minutes.
Well, we'll be about finishing up the.
Yeah. It's actually. Right. So I might just finish. Yeah, we'll not go into the application that I suggested. not because I think not that I wouldn't get through it, but I think it's already too much, I think. But all I can say here is that, so I just walked you through this unary case a little bit. Extending it to binary or arbitrary arity is not too bad. Actually, it's kind of funny because this is what Johansson-Tarski did originally. They have an operation on A, and that had to be monotone in all coordinates. And now when you play with it a little bit, you say, okay, so I can have some unary, some monotone, some antitone. But then what do we do? It's like, okay, so I can group all the antitones together. I can group all the monotones together, right? So that this gives me some lattice, I don't know, A1. This would give me lattice A2. This is lattice A3. So actually what turns out, and then I flip this around. So if that was all antitone, then I just make it monotone. And so if I just study all these operations that are of this form, you know, from in between three different lattices, and you play with it a little bit, you sort of describe arbitrary arity operations just from that. So that's in it's an extension to what the paper I have with Mygark and Rucarejo. So if you want to look at that, I've done that. It was a great discovery. I don't have to treat arbitrary arities that I can just do with binary multi-sorted operations. And then if you go to any of these places in the literature I mentioned, there you will find how this gives you semantics of intuitionistic logic, or duality theory for hiding algebras, or Salquist theory, Sakya, lemma, or all sorts of things you can do with this. It's extremely powerful. All right, I'll end with that.
Okay, thank you very much. So, any questions?
So do you have some nice description of this canonical extension of these Boolean algebras, like in the dual setting, like in topological spaces? So you have like a Boolean algebra embedded into a complete one in some special way. So in the dual setting, you would have this extremely disconnected topological space projected onto this other one. And is there some nice description, intuition behind that?
I don't know. Of course, if we think about what we have there, right? We have a Boolean algebra, right? Then you have the power set of right, ultra filters. So if we try to dualize fully, right, they would have stone space, projection, checkstone compactification, or that would be the thing that would make sense, right? The checkstone compactification of some discretization. That's what I would guess of X. I would guess that's what you get.
I was thinking more like applying the stone duality on the thing itself as is. So
yeah, that's right. But so this is precisely the checkstone compactification of that's what I just said. Yeah. But of course, I mean, for it to make sense, I would want you to do something like this, right? That would be some kind of so you would have a stone space, and that would be an extremally stone space that maps onto it such that something. Yeah, that's a good question. Maybe somebody has done it. I don't know.
Okay, thanks.
And have you seen anything like that anywhere else? I don't insist that it has to be described lattice theoretically, but sort of like having a structure and its dual in the same category. embedded into, having the structure, and its dual embedded in something bigger, which lives in the same category as the former, as the first structure. Gelfand duality, I don't know, something like that.
Well, yeah, I mean, you can, I don't know, if it's, so you could take a C-star algebra and look at its double dual, for example, and there's a natural embedding in the double dual, and this is a much larger C-star algebra, which is even, it's a von Neumann algebra, so it's completed the weak star topology. I'm not sure if you could say it definitely contains A, but does it contain the dual of A, or I mean, what exactly?
Yeah.
I mean, if you, I don't know, identify, I don't know, pure states with minimal projections, then I guess it kind of does contain the dual of A at the same time. But yeah.
Yeah, there's some discretization. Actually, when you look at what's going on, it's kind of interesting. So, all right. So you have Boolean algebras and stone spaces. Is this visible? And then here you have complete atomic Boolean algebras and sets, right? And you go to stone spaces, that's the ultra filter. Then you forget, that's you forget the topology. Then you build a power set, and then you forget that you were complete. That's another forgetful. So sort of forget twice. But here is an equivalence of categories, here is an equivalence of categories. So you have kind of correspondence between the two adjunctions or equivalences. Yeah. It's not just equivalence, it's also an adjunction. No, it's just the thing you compute, right? That's this B delta is what you get out of chasing this diagram. You get, this is the thing.
So yeah, another question then. So yeah, you did mention briefly you can start with, say, a distributive lattice instead of a Boolean algebra, and then you would look at, I guess, the stone space again of prime filters.
Yeah.
And then would you again just look at the power set of that to get this?
Yeah, you take the upsets in the specialization order.
The offsets in this.
It's the order of the priestly space. Take the upsets.
Okay. So your canonical extension in this case may not be atomic, or like it won't be.
Yeah, there is some description of that class of structures, but yeah. So this is about posets versus completely distributive lattices plus something, how they're generated.
Without being atomic necessarily.
Sorry?
But without being atomic necessarily,
I
right?
think something like that has to be there, but I'm not sure. Yeah, this is the thing, like with these things, complete atomic Boolean algebra, you can describe it in 7 different ways. And I know the one that corresponds to posets, or those that correspond to posets, by just taking the upsets, they are completely distributive. So arbitrary joins distribute over arbitrary means, but there might be some R stuff, I don't know. I have to look it up. Yeah.
Exactly.
Yeah, but maybe they're generated, not atomic. Yeah, atomic is something that you only see with Boolean algebras.
Meter reducibles. Or
Yeah, something like that.
Yeah.
Yes. Right. I'm not exactly sure, but I think it would be the completely meter reducibles.
Mhm.
But it might be that it's just completely distributive, and that's it. Because then you use the choice and you get that everything is generated by the meter reducibles, probably. Or, that's all you need.
Right.
Might be. Yeah.
Okay, well, if there's no more questions, then let's be going on.